Everybody, welcome to the session ECBS 2, Modeling and Analysis. And so the paper PSTM transaction scheduler verification based on CSP and testing is authored by Miroslav Popovic, Marko, Branislav, Kordic, and Huibiao. Okay, so this is the overview of the presentation, some introduction words, previous work analysis about the new model we made, and the formal verification we conducted, and we will end up with some conclusions. I'll try to squeeze my presentation a little bit so that we save a couple of minutes before the opening session. So we'll continue with the next slide. Okay, Python software transactional memory was formally verified with 3 complementary approaches using CSP, timed automata, and push-pull semantic model. And then on top of the Python software transactional memory, transaction scheduler architecture was created with the goal to minimize the makespan and maximize the throughput. And it can use one of the 4 scheduling algorithms. RR stands for round robin, ETLB is execution time load balancing, AC is avoid conflicts, and AAC advanced avoid conflicts algorithms. These algorithms were evaluated and their time complexity bounds were proved in the paper SG EE219. In the continuation of that work, in our previous work on TASET 219 conference, yes, we modeled PSTM scheduler architecture in CSP and CSP Sharp, which is a dialect of CSP for the model checker PAT. PAT stands for Process Analysis Toolkit. But when we wanted to compare the results of TASET 219 with SGA EE 219, we discovered some shortcomings in TASET 219. The main goal of this paper was to remedy and complete PSTM SA formal verification. So in this paper, we analyzed the previous CSP model, we correct and extend this model, we prove deadlock freeness and starvation freeness, and we analyze system performance from the perspective of makespan, speed up, number of aborts, and throughput. The analysis method we used comprises the following steps. First, we derive theoretical schedules. Then we calculate the makespan and the number of aborts. And in the third step, we compare the theoretical results with the results in the TASET 219 paper, which we will reference as 12. We use 3 workloads, CSW, which stands for conflict-free workload, and CW1 and CW2, which stands for conflict workload with level 1 and conflict workload level 2. In all the workloads, we have 5 transactions, which are designated T0 to T4. The duration of T0 is 50 time units, and the rest of them have 10 time units. They operate on 60 variables, which are labeled as A to F. The usage of T variables by transactions in the workloads is defined by these arrays, where the ith element of the array declares the variable which is used by a transaction. So each transaction uses just one variable, and here all the transactions use different variables, so it's a conflict-free workload. While in the second workload, 2 of transactions use variable A, and the other 2 variable B, so they have potential conflicts among themselves, and the transaction T4 uses C, so it doesn't conflict with any. And CW2 is created such that all the transactions operate on a same variable A, so they are all in conflict. So this is why this is the levels CF2. So the level of conflict is the highest in this last workload. So here, we will show how the theoretical schedules were derived. On top, we have an input queue of transactions, T0 to T4, which for the conflict-free workload operate on variables A, B, C, D, and D. And here are shown round-robin schedule, RR schedule on worker 0 and worker 1. So we will just show the schedules for the 2 workers. In the paper, we also consider other cases with 3 and 4 workers. And on the bottom of this figure is a schedule for ETLB, AC, and AAC schedule. So, I'm sorry, I'll have to talk more about this one. I'll just tell about it. Yes, so in the conflict-free workload, round-robin schedules the even transactions on worker 0 and the odd transactions on worker 1. And so this is the final schedule actually for that algorithm. But the ETLB and the AC and AAC create better schedule because they do the load balancing. And so here we have schedules for the CW1 workload, where the round robin again schedules all the even transactions on worker 0 and all the odd transactions on worker 1. But now there is a conflict between transaction 0 and transaction 1. Therefore, because transaction 1 is shorter, it will commit, while the transaction 0 will be aborted and re-executed in the second iteration of this schedule. So the cons of this schedule is that the load is unbalanced. Worker 0 has a lot to do, while worker 1 has just these 2 small transactions to execute. ETLB schedules transaction 0 on worker 0 and the rest of them on worker 1 because it wants to balance the load, and it does it. But now, same as in the case of the RR schedule, transaction 0, which is in conflict with transaction 1, gets re-executed. So the makespan for this schedule is 100 time units, and there is 1 abort. So pros of this schedule is that load is better balanced. So the makespan is also shorter. You see, makespan for the round robin was 120 units. The cons of the ETLB schedule is that still there is an abort, 1 abort. AC and AAC produce the same schedule because AC simple heuristic operate, in this case, very good, actually optimally, like the AAC schedule. Because these algorithms are aware of potential conflict between transaction 0 and transaction 1, they schedule both of these transactions to worker 0 and the rest of the remaining transactions to the worker 1. So now this schedule is conflict-free, and all the transactions end in 60 time units. So the makespan, the complete makespan is 60, and the number of aborts is 0. So pros, the advantages of this schedule over the previous schedules is that makespan is optimal, it's minimum. And also there's no conflicts, and we see the benefits of these more advanced algorithms on this test workload. The next and the last workload is conflict workload 2. It should appear soon on the here it is. So again, on top, we have an input queue of transactions. Round robin doesn't know about the conflicts. You see, all the transactions try to update a t variable A. So all of them are in conflict, but RR is unaware of this. It again schedules all the even transactions to worker 0 and all transactions to worker 1. Because T0 and T1 and also T3 are in conflict, but T1 and T3 end before the T0 and they are in sequence. So T1 and T3 get committed while T0 gets aborted and re-executed. The makespan is 50 plus 50 plus 2 times 10 is altogether 120 time units. And there was 1 conflict, T0 was re-executed. So again, in this third workload, we have an unbalanced load in the schedule, and there are aborts. ETLB is not aware about the conflicts, but it knows the durations of transactions. So it schedules transaction 0 on worker 0 and the rest of them on worker 1 in order to balance the load, and it does it quite good. All these T1 to T4 execute sequentially, so they all get committed, but T0 is in conflict with them and it ends later, so it gets aborted and re-executed. The total makespan is 2 times 50, which makes 100 time units, and there is one abort. So pros of this schedule over our schedule is that the load is better balanced, but con or disadvantage is that there is one abort. Finally, AC and AEC produce the same schedule, and because they are aware about the conflicts, they just serialize all the transactions. So they assign them to all of them to worker 0, while worker 1 remains unemployed. So it's just idle, it doesn't do anything. So the final makespan is 50 plus 4 times 10 is 90 altogether. There's no aborts. So pros of this schedule is that it's with minimum makespan. It cannot be done better than this because it's all the transactions are in conflict and there are no aborts. So in this way, we actually constructed this table, which shows 3 workloads we were talking about, and for each of them, 4 algorithms. And here in the first column, we have a makespan for each algorithm in each conflict and the number of aborts. When we tried to compare these expected theoretical results with the results from TASET 119 or reference 12, we see immediately that they are very different. So here we have a 1 second and some 30 milliseconds, and here are some unnamed time units. But these are not proportional. You see, these are 2 times two orders less these values. And here these values are in the same order. So also, if we look at number of aborts, here we expect just 1 abort, and we have here in previous work 6 and 7 aborts, and here 2. So we understood that something is wrong, and then we tested. We just manually inspected the model, the previous model, and found these limitations. So first, that time used actually metrics, which is time used by a model checker to check the assertions, was wrongly interpreted as a makespan. Another shortcoming is in the macro is conflict. We will talk about it soon. Then instead of using optimistic concurrency control in the model, it was modeled like pessimistic concurrency control. Also in the model, we saw that compositional processes was asynchronous instead of synchronous, because these processes execute on the cores with the same clock, and they must execute completely synchronously. Then the number of workers was fixed to 2, and the AEC algorithm was not supported. So here is how we fix the first shortcoming. The makespan for here designated as T infinity for the sequential compositional processes is just the sum of the makespans for the individual processes, while in the parallel composition, the makespan is the greater value of these 2, so it's maximum value. So we introduced the array load, and the ith element has a load of the worker VI. So it is actually a span of a series of transactions which execute on this worker, and so in the current iteration. At the end of the iteration in line 5, we find the maximum using the load 2, that is in line 6. So that's actually the span of the current iteration, and then we add this span to the iteration of the previous, to the makespan of the previous iterations. And this is how we calculate the makespan. Here is a conflict. Here is the macro is conflict, which checks whether the transaction X, which starts at T1 and ends at T2, is in conflict with previously scheduled transactions. And this is the algorithm how it's done. But in this algorithm, each transaction X was checking is it in conflict with itself. And so every transaction was in conflict with itself. So we just added this condition in order to skip checking conflict between the transaction X and itself. We modeled optimistic concurrency control by modeling a PSTM. So we model by this array TVAR version, and its yacht element, it contains the version of TVAR-J, a dictionary of the PSTM. And the PSTM process receives a message from the worker over the channel worker to PSTM. This composite message has an index of the worker, request, which can be a get vars or commit vars, key of the T variable and its version. If its request is the get variable vars, then PSTM just returns the version, current version of that T variable to the worker over this channel. Otherwise, it checks whether the versions are the same, so is still actual. If it is, then it updates the version, current version, and returns one, which means that it was successful, that is successful commit. Otherwise, it returns 0, indicating abort. Synchronous transaction execution is modeled like using the synchronous execution of the processes, where the workers must perform the same number of ticks, which is designated as NT. The number of ticks for the worker I is calculated as its load plus number of transactions in its input queue. And the maximum of NTI is actually this number of ticks that every worker has to perform. So after executing all the transactions, worker VI has to execute some idle ticks, which is calculated, the number of idle ticks is calculated as NT minus NTI. The process working models the beginning of transaction, while working _1 models the end of the transaction. And in the process worker _2, the worker just counts the idle ticks. Right, so we come to the formal verification where we just introduce some new symbols. S_num is the number of successful transactions. Then we have 3 conditions. Done requires that this number of transactions is equal to num, which is a constant defining the number of transactions in the workload, which is actually here 5 for all 3 workloads. Max NA requires done, and that number of aborts is non-negative, while max MS requires done, and that makespan is non-negative. We proved 5 assertions. First is deadlock freeness, and the next 4 are actually proving starvation freeness. The second assertion is the system reaches a state satisfying condition done. Third, always eventually signal complete is sent to the application. So all the paths in the state space are analyzed, and in all of them, eventually this final signal is sent. The fourth assertion is the system reaches a state satisfying condition max NA. And we also require a path to report maximum number of aborts. This is how we actually get number of aborts from path. In the fifth assertion, system reaches a state satisfying condition max MS, and we require from path to report maximum makespan. Here is a table of expected values for makespan and number of aborts for 3 and 4 workloads. In the verification, we have the following system versions for the 3 cases with 2, 3, or 4 workers, number of workers, 4 algorithms. 3 times 4 makes 12 system versions. For each system version, we checked these 5 assertions. So 5 times 12, altogether 60 versions for each test workload. And times 3, 180 altogether assertions were proved to be correct. The heaviest case was for the 4 workers round-robin algorithm and conflict-free conflict workload level 1, where PAT visited 6 million states, 35 million transitions. The verification process lasted 219 seconds, and the PAT model checker used 7 terabytes of operating memory. Then we analyzed the average makespan. Here in the table, the rows correspond to the NIT, which stands for the number of independent transactions. And this is defined as the number of transactions which can be scheduled in parallel without conflict. So in the conflict workload 2, this is just one. We can schedule 1 transaction. In conflict in CV 1, we can schedule 3 transactions, and in conflict-free workload we can schedule all 5 transactions. Then with MSXX we designated the average makespan for each algorithm XX, where average is calculated over the 3 cases for the 3, 4, or 5, 2, 3, or 4 workloads. The results are these columns, which are illustrated in this figure. The smaller makespan means better, smaller values, so it's faster executed. And the results are expected because as the number of independent transactions increases, the makespan decreases in all the cases for all the algorithms. And the overall rank, we read from bottom, and the best is AAC, then AC, ETLB, and RR is the worst. Similarly, we analyzed the throughput of the system. Here is the table with the results. Results are again as expected because higher values means better, higher throughput. And as number of independent transactions increases, the throughput increases for all the algorithms. The rank list for the algorithms is again AAC is the best, AAC, ETLB, and RR is the worst. So an important lesson learned in this research is that using formal methods in isolation is not sufficient. We saw all these limitations that were made using this approach. So in this paper, we jointly use both formal verification and its testing. The key idea is that we analyze the previous CSP model by testing the model checker path results, and then we manually inspected the relevant parts of the model. Limitation of this paper is that verification is based on 3 particular workloads, and that each transaction in these workloads operates just on a single T variable. So in future, we plan to introduce workloads from our initial research and to try to compare the results with the initial research. Okay, thank you for your attention. And so we can switch to questions if there are any.